On July 21st, 2023, at NASA's Jet Propulsion Laboratory in Pasadena, California, an engineer sent a routine command to Voyager 2, the kind of command the team had been sending for 46 years. A planned software uplink, part of the ordinary maintenance of a spacecraft that had traveled further from Earth than anything humanity had ever built. Something in that command was wrong. Within hours, the Deep Space Network's vast dish antennas, including the 70-meter radio telescope in Canberra, Australia, one of the most sensitive receivers ever constructed, swept the sky for Voyager 2's signal. The frequency they had been listening to for decades, the one that had never, not once in 46 years, gone completely dark. Nothing came back. Voyager 2 was 12.3 billion miles from Earth. Its signal, even under normal conditions, was fainter than a digital watch battery powering a transmitter visible from across the solar system. Now that signal was gone. And the team at JPL knew something that made the yes silence much worse than it might seem. Without a signal coming in, they also could not send commands out. The same antenna that had gone deaf to Earth was also mute. Voyager 2 was effectively unreachable. The crisis began with what should have been a standard software uplink. Inadvertently, the team sent the wrong version, causing the high-gain antenna, the critical link for all data, to veer off Earth's direction by just 2 degrees. That tiny misalignment was enough to cut off both telemetry and command capability, leaving Voyager 2 effectively deaf and mute. 2 degrees? At 12.3 billion miles, 2 degrees of antenna misalignment is not a small rounding error. It is the difference between a spacecraft that is pointing its transmitter directly at Earth and one that is broadcasting into empty space, past Earth, speaking to no one. The physical geometry of deep space communication leaves no margin for error. The antenna has to point to where Earth is, not approximately, not close, exactly. The team at JPL had one immediate hope and one fallback. The hope was that Voyager 2's onboard fault protection software, the autonomous emergency code written into its 1970s-era computer, designed to handle exactly this kind of situation without needing instructions from Earth, would trigger a reset and reorient the antenna automatically. But the fault protection system had a problem of its own. It wasn't scheduled to run its orientation reset until October 15th, nearly 3 months away. Voyager 2 is programmed to reset its orientation multiple times each year to keep its antenna pointing at Earth. The next reset was scheduled for October 15th, which should enable communication to resume. The mission team expected Voyager 2 to remain on its planned trajectory during the quiet period. 3 months. The spacecraft would keep traveling, it would keep collecting data with its instruments, it would keep doing everything it was built to do autonomously, and without any confirmation from the people who built it. But none of that data would go anywhere. And none of the engineering telemetry that told JPL whether the spacecraft was healthy would reach Earth either. 3 months of silence from a machine 12 billion miles away, running on less power than a refrigerator light bulb, with no confirmation that anything was working. A tense silence descended upon mission control. The vastness of space suddenly felt even more profound and isolating. The team at JPL grappled with the chilling reality that their intrepid explorer might be lost forever. Panic was not an option. The engineers and scientists behind the Voyager program were veterans of deep space challenges. They knew that reestablishing contact required patience, precision, and an intimate understanding of the probe's capabilities. The fundamental problem was not complicated, but the solution was. The antenna was pointing 2 degrees off. To fix that, you needed to send a command to reorient the antenna. To send a command, you needed the antenna to be pointing toward Earth to receive it. A circular problem with no obvious solution, 12 billion miles from the nearest human being. The Deep Space Network operates the largest and most sensitive radio antenna system humanity has ever built. Its primary facilities in California, Spain, and Australia use dish antennas up to 70 meters in diameter, built to detect signals so faint that they would make the concept of a whisper sound thunderous by comparison. Under normal operating conditions, Voyager 2's signal arrives at Earth with a power of approximately 10 billion times weaker than a mobile phone transmission. The DSN captures it because its antennas are engineered to be extraordinarily sensitive, but sensitivity works in both directions. If the antennas are sensitive enough to hear a signal that faint, could they be made powerful enough to send a signal loud enough to reach a spacecraft pointing slightly the wrong way? A spacecraft whose receiver was technically facing almost, but not quite, away from Earth. The team spent days analyzing the geometry, the receiver sensitivity on Voyager 2's end, and the maximum transmission power available from the DSN. Then they made a decision. On August 2nd, the Deep Space Network's Canberra station fired a 100-kilowatt S-band signal directly at Voyager 2. With an 18.5-hour one-way light time, the team waited anxiously for 37 hours to learn whether it had worked. 100 kilowatts, fired across 12.3 billion miles of empty space, aimed at an antenna pointed 2 degrees in the wrong direction, hoping that the signal would be just barely strong enough to spill around the edges of the misalignment, to be detectable by Voyager 2's receiver, to be recognizable as the command it encoded. Then they waited. 18.5 hours for the signal to arrive. 18.5 hours for any response to come back. 37 hours total. In mission control, that is 37 hours during which the question has an answer. Yes or no, it worked or it didn't, but no human being on Earth knows what that answer is. At 12:29 a.m. EDT on August 4th, the spacecraft began returning. Science and telemetry data indicating it is operating normally and that it remains on its expected trajectory. Operating normally, that was the first word. Not damaged, not in fault mode, not partially functioning. Normally. The spacecraft that had been broadcasting into empty space for 2 weeks while its controllers on Earth couldn't reach it had been operating normally the entire time. Its instruments were still running. Its trajectory was precisely where it was calculated to be. Its subsystems were all within normal parameters. The silence had been one-sided. JPL had lost contact with Voyager 2, but Voyager 2 had never lost itself. The hiatus was the longest silent interval in Voyager's mission. Mission scientists were not unduly alarmed about scientific data loss. The probe is studying interstellar space across long timescales, so missing a few weeks of data posed no long-term scientific loss. But here's where the story shifts from recovery to revelation. Because what the restored data link carried back to Earth was not simply confirmation that the spacecraft survived 2 weeks of silence, it was a continuation of a scientific record that, in the moment of restoration, contained something the team hadn't expected: the plasma density readings. Voyager 2 carries the only functioning plasma science experiment in interstellar space, the instrument that Voyager 1 lost to a short circuit in 1980, 32 years before it crossed the heliopause. During the 2 weeks of silence, this instrument had continued making measurements, storing them in the spacecraft's data buffer, waiting for a communications link to return them to Earth. When contact was restored in the early hours of August 4th, that buffer downloaded, and the data it contained showed something that the team immediately recognized as significant. The plasma density in the region Voyager 2 had been traveling through was higher than in the region it had occupied before the silence began. Not dramatically. The outer heliosheath through which Voyager 2 is traveling doesn't change character over the course of 2 weeks. But the incremental increase was real, consistent with what earlier readings had been suggesting, and it confirmed something about the structure of the region beyond the heliopause that the models hadn't fully accounted for. The interstellar medium, the space between the stars that Voyager 2 is now traveling through, is not uniform. It is not a calm, even ocean of ancient galactic gas. It is denser closer to the heliopause, compressed by the presence of the heliosphere pushing outward against it, and that compression appears to extend significantly further from the heliopause boundary than theoretical models had predicted. The data Voyager 2 was collecting during its 2 weeks of silence, and which returned to Earth in the burst of restored telemetry on August 4th, added 2 more weeks of measurements to a baseline that is slowly but definitively revealing the structure of the outer heliosheath in ways that cannot be observed from inside the solar system. The episode also changed something at JPL, not in the data, but in the thinking. The incident highlighted the need for robust contingency planning and the invaluable expertise of the teams who dedicate their lives to these far-flung missions. What made this event particularly poignant was its timing. Voyager 2's power supply was already declining at the steady, inevitable pace of 4 watts per year. The instruments were already being powered down one by one to keep the most important ones running. The July 2023 silence was a vivid demonstration of exactly how close the mission always is to the edge, how a single misdirected command, at a distance where the round-trip time for any correction is measured in days, can sever humanity's link to the most distant scientific instrument we have ever deployed. The lesson landed. Within months, the mission team had developed more rigorous command verification protocols. The process of reviewing and confirming each command, sequence before it was transmitted, was tightened to specifically catch the class of error that had caused the July 2023 incident. And, in the longer strategic picture, the incident accelerated conversations about what the mission's final years should look like, which instruments mattered most, which power trade-offs were acceptable, and what engineering gambles might be worth taking to extend the life of a scientific resource that has no replacement in any timeline a human generation can see. Those conversations produced, eventually, what JPL now calls the Big Bang. The team will implement the Big Bang on Voyager 2 first, which has a little more power to spare and is closer to Earth, making it the safer test subject. Tests are planned for May and June 2026. If they go well, the team will attempt the same fix on Voyager 1 no sooner than July. If it works, there's even a chance that Voyager 1's LECP could be switched back on. The Big Bang is, in structural terms, the most ambitious engineering maneuver the Voyager mission has attempted in decades. By swapping several aging components for lower power alternatives and turning off certain fuel line heaters, engineers hope to find an extra 10 watts of power. The risk? If the fuel lines freeze, the probes can know. Longer point their antennas at Earth, 10 watts. On a spacecraft currently running on approximately 230 watts total, with roughly 200 watts needed just to keep the transmitter and basic systems operating, finding 10 watts through clever power redistribution is the difference between keeping a science instrument alive and losing it. The LECP was the only instrument providing direct, in situ, measurements of low energy, charged particles in interstellar space, crucial for mapping the heliopause and understanding solar-wind interactions with the interstellar medium. Matt Hill, principal investigator for the instrument at the Johns Hopkins Applied Physics Laboratory, wrote, "We hold out hope that the Voyager engineers' latest plan will be able to power up LECP on Voyager 1 again to let us continue to learn whatever surprises await Voyager in these distant regions of space. They have a good track record of seeming to perform miracles that stretch the remaining power supply, but eventually this streak will end." Voyager 2 was chosen as the test platform specifically because of the lesson from 2023. It is slightly closer to Earth. The round-trip communication time is about 28 hours versus 46 hours for Voyager 1. That extra 18 hours of response time matters enormously when you're reconfiguring critical power systems on a spacecraft with no human engineer within 13 billion miles of it. If something goes wrong during the Big Bang maneuver on Voyager 2, the team has a slightly tighter feedback loop to diagnose and respond. The July 2023 incident demonstrated, with brutal clarity, what slightly tighter means at interstellar distances. It means 37 hours to know whether a single command worked instead of 46. It is a narrow margin. But in this mission, narrow margins are all there is. The Voyager 2. Big Bang tests ran in May and June 2026. As of July 2026, the team has not made a public announcement of the results, which could mean the tests are still being analyzed, or that the team is completing verification before committing to the Voyager 1 implementation. What the mission's own statements confirm is that Voyager 2's plasma instrument, the one that fell silent for 2 weeks in July 2023 and came back with data showing the interstellar medium getting denser as the spacecraft moves deeper into it, is still running as of mid-2026. Still the only direct plasma measurement device in interstellar space, still transmitting, still the irreplaceable scientific instrument at the center of everything this mission has produced since 2018. The silence of July 2023 lasted 13 days. The engineering shout that ended it crossed 12.3 billion miles in 18.5 hours, fired at 100 kilowatts from a dish in Canberra, and found a spacecraft that had been operating normally all along, collecting data about the interstellar medium in the dark, patiently waiting for the conversation to resume. When the data came back, it added 2 weeks of plasma density measurements to a record that has been steadily building since November 2018. It showed a denser outer heliosheath than models had calculated. It extended the map of interstellar space one data point at a time, as it has done every day for the 6 years since the crossing. NASA said Friday that it lost contact with Voyager 2 on July 21st, after a series of planned commands inadvertently caused the craft to turn its antenna 2 degrees away from Earth. What might seem like a slight error had big consequences. 2 degrees at 12 billion miles, a 100 kilowatt shout across space, 37 hours of waiting. And then, at 12:29 in the morning on August 4th, 2023, the data began streaming in again, still there, still measuring, still finding things that weren't in the textbooks. The silence changed how the team works. The data that broke it changed what we know about the space between the stars. And the instrument that held the silence and kept recording anyway, Voyager 2's plasma science experiment, the one Voyager 1 lost in 1980 and never got back, is still running right now, 13.4 billion miles from Earth, transmitting a signal thinner than a whisper across a distance that takes light nearly an entire day to cross. Subscribe, because the Big Bang results for Voyager 2 are due any time now, and whether that plasma instrument survives what comes next is the most consequential question in deep space science right now.